Okay, I'll do a cross multiply, and then I take the first variation by variational calculus, very much like what I do here. So if I take the first variation about the exact solution, the auxiliary problem have an exact solution. Okay, those first term will give me that, and then I will have U exact. Okay, I take the first variation, delta F FA, L F exact plus FA exact L delta F. This is the first variation I get of the left-hand side. Okay, and then the first variation on the right-hand side will be just delta F, comma A G H F exact. Okay, for the first term, and then F A exact G H delta F. Okay, so taking the first variation, I get that. If you can prove that this term cancels everything on the right hand side, I would be able to prove that delta U is equal to 0. Okay, let me prove that this thing in fact cancel each other. Okay, this thing in fact cancel each other. I know that this thing can be written as delta FA. What is LFE exact equal to? LF exact equal to? What can I replace it with? Given that the original problem I want to solve is LF equal to G, right? I define an auxiliary problem. So LF exact will be equal to G, right? So that should be equal to that. And then if L is symmetric, I can rewrite this term as delta F L F A exact, right? I can put the L operator on the LFA exact, but LFA exact would be equal to H. So this would be delta F comma H, right? So I simplify the left-hand side.
Why do you use different notations?
What is that? Different notation for what?
For exact?
No,
F subscript AE, auxiliary problem.
Yeah, I have two problems to solve. This is one problem, and this is the second problem. Assume that I have found the exact solution to this equation.
No. So there is LF subscript A, right?
Right.
And then you have an AE. What is that?
Oh. This is the exact solution, right? FA, I let the transpose of this operate on this exact solution, I get this, right? I'm just rewriting this. Let it operate on this. This becomes that. Okay? And if this is the exact solution, this must be exactly equal to that. So this becomes that. And let me see, I can convince you that all the terms cancel each other. Okay, all the terms should cancel each other. And I can also make use of the fact that so what I can convince you is that this term cancel each other if UE, okay, delta FA G would be equal to delta FA G H FE, right? If it convince you that this would cancel each other, and how can I convince you that this cancel each other? I can convince you by using this equation over here, right? That if I go back to this equation, if I have the exact solution, I will have UE equal to FA exact G H F exact And then if I have the exact solution, this LF will be equal to G. This will be F A exact G, right? So this would be just equal to HFE. Okay? U exact would be just HFE. Right? Can you see that? U exact, if I go back to this equation, is just equal to this quantity. This is the goal of this variation expression. So if that is the case, then this cancels that one. Right? And then this equals that. So I proved to you that this term is exactly equal to this term. By the same token, you can also prove that this term is exactly equal to that term. And then this term would cancel everything on the right hand side. Okay, finally the conclusion is that delta U is equal to 0. So Jones have defined a quotient so that delta U is equal to 0 if there's a first order error in delta F and delta F auxiliary. Okay, if you solve the auxiliary problem and the original problem with an approximate solution, if you plug the calculation to the Jones quotient, your calculated function L should have a second order error. Okay, it's variational in that sense. Okay, does everybody get it? So in the future, if you want to calculate certain quantities, and if you like to improve on its accuracy, you can use this idea to improve on the accuracy of your number, the scalar number that you want to calculate. Okay? But what does it mean? What does it mean actually? What does it mean actually? It means that you have to solve the original problem plus the auxiliary problem accurately enough so that this error is small. If this error is small, this is even smaller. So what does it mean by solving the auxiliary problem? We can think of H. H has been, say in a one-dimensional problem, Hx can be delta x minus x0. So that U is Hf, and in one-dimensional case, is the solution at a given point in space that if you have, after having solved the solution for f, I'm only interested in the solution at one particular point. I want the solution there to be as accurately as possible. Okay. How can I improve the procedure so that the solution here is the best? What it means is that I have to solve this auxiliary problem. Is equal to Hx, right? Is equal to delta x minus x naught. So I'm actually solving something very similar to the original problem, except that the right-hand side has been replaced by a delta function source at that point of the thing. Okay, for those of you who are familiar with numerical methods, if I want to solve, say, this differential equation accurately at this point, what is the best way to get an accurate solution at that point? If I say I solve it with finite element, I do grid refinement, right? I try to refine the measure of the thing. So I will try to find a way of solving this problem so that the solution is very accurate there. And then I will have a good way of calculating the solution this way and get second order error with my problem. Okay? So we have talked about variational expressions of the reaction kind, the energy kind, as well as the Jones quotient. There's another quotient called the Rayleigh quotient that I will talk about later, which is also variational, and that is quite popular in quantum mechanics, which is the case of the Rayleigh quotient. But then, once we have these variational expressions, what can we do with them? We can use them to motivate how we can actually solve a problem like this accurately. Okay. We know how to convert this into a matrix equation in a verbatim fashion, in a kind of straightforward fashion, by just using expansion and testing. We expand the solution in terms of a basis set, we test this equation with a weighting function, and then we obtain this equation. But the variation expression will give you a guide as to how to do the testing and how to do the expansions correctly. Okay, let's see if we can get such a guidance by studying the use of the variation expression to solve a standard problem. And the procedure is usually called a Rayleigh-Riggs procedure. A Rayleigh-Riggs procedure. I'm sure that many of you have heard of this procedure before. And let's do the case of the okay, let me step back a little bit. I think the symmetric case is quite straightforward, but let's do the case of an asymmetric problem, non-symmetric problem. Okay, you can do it for non-self-adjoint, which is kind of interesting. The case of symmetric problem is quite straightforward, and then self-adjoint problem is also quite straightforward. Okay. So let's do the more interesting case of the non-symmetric problem, where the L operator is not symmetric. In that case, in electromagnetics, with an operator that is not symmetric, it corresponds to a problem that is not reciprocal. Okay, when the problem is not reciprocal, then you have non-symmetric problems. Let's do the case of the non-symmetric case. In that case, if the problem is non-symmetric, solving the original problem is not enough, because L is not symmetric. You have to solve the auxiliary problem, which consists of solving this problem as an auxiliary problem. Is auxiliary spelled with one L or two L's? Two L's? Okay, so I have to put an extra L in. Okay. So for the case of a symmetric problem, you don't have to do this, because the transpose of this operator is itself. Okay? And essentially, if a matrix system like A is not symmetric, then if you have A dot X, this is called the domain of A. Okay? If the system is non-symmetric, then this is called the domain of A transpose. What it says essentially is that the domain space of the L operators are not the same. A and A transpose. This and its transpose. Or this two operators have different domain space. If it's a symmetric operator, the domain space will be the same. The domain is the space of vectors that the operator acts on. Okay? They will have different domain space. So we have to keep track of the solution of the domain space of the transpose operator as well as the original operator. Okay? And I just want to mention the fact that in that case, the linear function now that minimizes or optimizes this 2 problem is such a functional. You can define a linear functional. If L is symmetric, then we can choose G equals GA. L transpose will be itself, and then this reduced F equals FA. Then it becomes the functional that we had just studied a while ago. Okay. But I'm going to generalize this to the case when L is not symmetric and see what we can do with it. You can take the first variation of this and show that the first variation of I would be 0 if F and F adjoint satisfy these 2 equations. It's very easy. You just go through the exercise, you can prove it. I don't have to prove it to you, right? You just take my word for it. Okay? And so this is variational. I'm not going to prove it, but you can prove it yourself. And then we apply Rayleigh-Ritz procedure. Let's do that after the coffee break. Okay, we take a 5 minutes coffee break, and then come back and solve this general asymmetric or non-symmetric problem, and see how we get a solution out of it. Okay, we take a break.